I said howdy. Howdy. All right. I love it when the audience shows up. OK, we're going to talk about Cloud Native Buildpacks today. This is a tool for generating Docker images from your application source code. But it's a higher level abstraction than Dockerfile, and it's really oriented towards application developers. My name is Joe Kutner. I go by Codefinger online. I work at Heroku, where I am an architect on the languages team. I work a lot in the Java ecosystem, and I run the Java experience on Heroku. With me is my more stylish friend and coworker, Terence Lee. He works at Heroku, too. He has been there longer than me and co-created Heroku Buildpacks a number of years ago. We're going to talk about that in a little bit. So yeah, we both work at Heroku, which is a platform as a service. It's often considered the first platform as a service. We kind of created that type of cloud product. We host more than 7 million applications and handle roughly 23 billion requests per day. We created a technology called Buildpacks that we're going to talk about today, a little bit about its history and a little bit about where we want to take it.
So we're all here at KubeCon, and Kubernetes is a great platform to run and orchestrate images. But there's no kind of prescriptive way on how you actually build them, right? Kubernetes does not provide a standardized way to actually construct the images. They just care about getting the images and actually running them. And really only the game in town is Docker, right? Like Docker is kind of the standardized way that people kind of started this whole trend of containers in this ecosystem. And it's the main way that most people build images. It's the state of the art of how people do things today. You take a Docker file and you actually build it with the Docker tooling. And so to start off this talk, we're going to go through and containerize a really simple Ruby application and then kind of move on from there. And so if you go on the internet and you go search for how you go about doing this, you probably end up with some file that looks pretty close to this, right? Like you inherit from one of the official Ruby Docker images that provides you with a Ruby runtime. You're going to copy your app source code into the container. You need to install your dependencies. If it's a web app, you want to be able to expose a port into the container itself so you can actually get stuff out of it. And then you need the command that's actually going to run the Ruby application itself. And with that, we use the CLI from Docker, run Docker build, and it goes ahead and for every single step will produce a layer for everything that it's done. And at the end of it, you get a Docker image that you can run with Docker tooling. You can run with Kubernetes. It's now a portable format that you can actually do stuff with. So pretty simple. That was a pretty contrived example, right? You're not actually going to ship that thing to production. So if you're running a Ruby application, you're probably going to be building something in Rails most likely. Ruby on Rails is kind of the major web framework in the Ruby ecosystem. And so if we wanted to go and extend that existing example for Rails, what does that look like? So if I'm building a web application, I need to install some other dependencies that aren't part of the base Docker image, right? So I'm going to install Node.js because I want to be able to compile assets, which I'm doing later down with the rake assets precompile. But I need a Node runtime to actually go and compile that, right? Like all the state-of-the-art front-end stuff is done in Node. I also need to be able to talk to a database of some sort, right? So in this example, we're going to be doing stuff with Postgres. So I'm going to install libpq, the dev headers, because in Ruby, those are native extensions that link against the development headers. And none of that is part of the base image, so we need to install that. And of course, to actually build any native extensions, I need to have Build Essential to actually get GCC and automake and all that stuff. So with those things, I now have all the dependencies to actually go about and actually compile a full Rails app. And then the asset compilation that I touched on before will actually build the assets that can get statically served. And then with that image, we can actually run this thing in production. But you probably don't actually want to use that image as kind of what you're using to deploy to production, right? There's some other best practices if you've been doing Docker stuff for a while that you're probably used to, of reducing the image size, making sure incremental builds are faster, and kind of thinking about the different decisions when you're picking your various base images and whatnot. So like I was saying before, like each step produces a layer inside of Docker. And one of the distinctions there is that with the Dockerfile layers, you get this nice caching thing that Docker has done where basically if there are changes that happen at a specific layer, all the layers above it, you just get to use all the existing layers of it. But any change that happens afterwards, you bust the cache and have to rerun those steps from that one and below. And so what we can do with like image sizes is like when we're installing dependencies, you probably want to go ahead and actually like clean up your app stuff because you don't actually need or want that in your production image at the end. And similarly with like assets precompile, you're going to cache. There's going to be a cache that's used normally when you're doing development to speed up asset compilation between some sequent builds, but we don't need that cache like in our resulting Docker image. So within those steps, in order not to create existing layers, because the more layers you have, the more layers you have to pull down, we're going to add that into one single step for each thing that we're doing here. So that will make the steps smaller. And in addition, in order to speed builds, this is I think a simple hack that every language does, but for like dependency management, you want to extract that into a separate step. So most of the time you're not adding new dependencies, so you don't want to actually rerun all the dependency installation every time you change any app source code. So we're going to hoist that into a step above the rest of adding the rest for application. So that should speed up our incremental builds for our day-to-day development. And in addition, on this first line, we have that command from Ruby. And there's actually a bunch of decisions you have to make with that because the base image that you're inheriting from actually has a bunch of implications, right? So if we go to the Docker Hub page, there's, even for a single line, there's like 5 or 6 different images that you can pick from. And each of these, like if you're doing Alpine, because it's like a small image, or Debian Slim or something, or Debian Stretch, there's different security implications of how those operating systems get run and how those patches get applied and how you actually keep track of those. So those are things that you have to keep track of as you're making decisions for your Dockerfile. And so here's a quote from a friend of mine. He runs CCO of Convox, and Convox is basically a Docker platform as a service. Like all these things I talked about are all these decisions you have to make as part of your build pipeline, right? And so even for a person who runs a PaaS for a Docker platform, basically, the hardest part is actually writing a quality Docker file that produces a small image that is fast, right? Like there's all these best practices you have to keep track of.
Yeah, so despite being the state of the art for generating Docker images, Dockerfile has some shortcomings. And this really stems from the fact that it's not app aware. It doesn't know anything about the context of your application, the frameworks you're using, what your application is doing. And the result is sort of an impedance mismatch between application developers and the tool they're using. So this is really best illustrated when it comes to maintenance or day 2 operations. So when you're using Dockerfile, an application developer now has to be acutely aware of the operating system that they're running on and the packages that it contains, whereas before Docker, that wasn't necessarily a concern. So when there's a vulnerability like Meltdown, where all of your operating systems need to be updated, you need to methodically go through your apps, update their Docker files, and rebuild them. We worked with a customer who has about 40 applications, and this process takes them more than 3 hours just to rebuild the applications, not even to roll them out to the fleet. We also see this when it comes to combining different types of runtimes and ecosystems. So composability is a real weak point of Dockerfile. If you have 2 Docker images, for example, if I have my Ruby image that we kind of walked through, and then I want to use Java for something, like to parse XML or to do something with Kafka, I want to combine the OpenJDK image, the official OpenJDK image, with the official Ruby image. But the only mechanism I have to do that today is multi-stage builds. So this is what that might start to look like. I'd take my OpenJDK image, I'd do my Java Maven stuff, and then I'd go to my Ruby image and I'd do a copy from, and I'd copy that Docker Java home directory. But there's a problem. That Docker Java home directory is actually a symlink, and inside of that directory are more symlinks, and copy from doesn't follow symlinks. So I actually have to copy a bunch of other directories, and I have to know what those directories are. I have to copy my certificate bundle and some configuration. I also have to copy the binaries themselves from user bin. So there's a whole bunch of knowledge I need to have about what that image looks like. Multi-stage builds don't do anything for environment variables, so I actually have to manually set those environment variables from the previous stage as well. Oh, but I need my application stuff too. So I also have to copy that target directory, the output of the Maven build that has my dependencies and my compiled code. I've got to copy that into my main Ruby image, and I want to do it in a way that doesn't bust the cache, that doesn't invalidate all the layers if I update my Maven or Java. OK, so this will work. But there's one more problem. The JDK is meant for compiling code and doing things at build time, but I don't want it in production because that'll increase my security surface area. So I actually want the JRE. So I need a stage for the JDK. I run Maven, compile Java, and then I go to the JRE, and that's the one that I copy in. And now I have I've composed these two images. So as you can see, this is kind of a cumbersome process. It requires a lot of knowledge about the other image that you're trying to compose with. So just to recap, the composability of multi-stage builds lacks support for environment variables, symlinks, and it really only allows you to copy specific directories. You can't copy like arbitrarily named directories, maybe something that's based off of a UUID or an incremental number. The end result is really a leaky abstraction. In order for an application developer to write a Docker file, they need to understand intimately how Dockerfile works, how it produces these layers, and what the underlying mechanisms are doing. And the result is just a poor tool for people who really just want to write code, build features, and deliver value for their customers. It also mixes operational concerns with application concerns. So given these deficiencies, what are the alternatives? We're starting to see a few things come about. There's Jib, which is a Java-specific tool. It integrates with Maven for producing Docker images from your Maven build. There's FTL, faster than light, from Google. And of course, there's Buildpacks, which we're going to talk about.
So Cloud Native Buildpacks is a project that is part of the Cloud Native Sandbox fairly recently. We've been working on this project probably a little over a year now at this point, and there's been contributions from both Heroku and the Pivotal side. And we've been bringing kind of expertise of us running Buildpacks in production for a long time together, which is exciting. And Joe was talking about basically like all the things that you kind of didn't have to worry about before the container days. And Heroku was this PaaS that really got started with this one command, git push Heroku master. And what was the beauty of this was back in the day, like this was when, if you kind of go back in time, you have to think about like, oh, I went and like SSH into my production server, pulled down my code, ran my production stuff like on production. And one of the really transformative things about git push Heroku master is it set up this part where you would do these independent builds, right? Like so Heroku would have a separate build service that would build it, and then you'd run this thing in production. They were two separate machines. And for there's all these concerns we're talking about when you're running Docker. For all of our customers back rewind like 8-ish years ago, this was the only command they had to do to take their app source code that they had working on the machine, run this command, and they would have it running in the cloud. And so they didn't have to worry about all the things that we just talked about with Dockerfile. And at the heart of that is this technology that we created in 2011 called Buildpacks. And we used it to basically launch our polyglot platform. So we went from a Ruby-specific platform to a platform that supported really any language. And the way we did that was Buildpacks were a way that we could have this opinionated, app-aware, source-agnostic way to build your application. So you provide your app source code, and the Buildpack would do all the language-specific things that we needed to kind of munge your app source code into a artifact that we could actually run on our machines. And so we would have Buildpack specific for, at this point we have 6 supported languages, but you would do like, we'd have one for Ruby, for Node, Python, Java, et cetera. And the way Buildpacks work is a Buildpack is really just made up of 3 different files. And so inside of a bin folder, you have detect, compile, and release. And detect simply just decides if we need to run this Buildpack or not. So we can run this thing and determine if this is a Ruby app, if this is a Java app, et cetera. The compile would do the bulk of the work of actually going and fetching the runtime, the compilers, installing your dependencies, and all that stuff. And then release goes and actually just sets up other metadata about your application, right? So you could set like default commands that you would need to run. So I don't have to necessarily go ahead and kind of hard code all those things into my application. And once you're done running your application, what you get, we call a slug, but it's really just a read-only tarball of your image that we can run on any single machine. And so so all this stuff runs on what we call stack images or base images in the Docker sense. And at Heroku, they're all based off of Ubuntu from Canonical, and we do them for all the LTS releases. So as you do upgrades for a particular LTS release, as long as you're staying within that release, there's an ABI compatibility between the tarball. So what that means is that when we're doing stack image upgrades, unlike Docker, we don't actually have to go and rebuild the app itself, right? So we can just apply these updates to the stack image and then take that existing tarball that we have and just run that on the new stack image. And so we've been doing this in production for our customers for 8 years or so at this point, and I think Pivotal is probably something similar like that as well. And we've run into pretty much like no incidents from doing it this way because of the guarantees that these distros provide us. And so digging into we did that Ruby example. So what does a Ruby build pack do in comparison, right? So it's going to do a lot of the same stuff. So instead of having a from line, we're going to actually install the Ruby binary for you. We're going to set the dependencies and kind of configure your application to make sure it can run. So all the stuff it has to do to make Rails run, like compiling assets, setting up your database, all those things that you would normally have to do on top of your existing Dockerfile, the build pack handles that. And it also does comprehensive support, right? So this means that for the last 7+ years that it's been out in production, people have used this build pack by itself, right? So we support these various versions of Ruby on the platform from the latest release, which is 2.6.0 RC1 that launched a few weeks ago. So the same day it comes out, you can run it on Heroku using this build pack all the way down to these old releases, and you get to use the same build pack. So normally in Docker, you would have to use a different Docker image, rebuild your app, right? And on Heroku, it means that when you're using a build pack, as a user, you don't have to worry about these things. You get to use the same build pack for all these different things, and you don't have to worry about which Docker image do I need to use for that stuff. And this has been used in production by millions of applications on the platform today. And in 2012, we actually open sourced the Buildpack API, all of our build packs, and this led to the creation of this entire build pack ecosystem. So we support 6 to 8 languages officially on the platform, but there's been other stuff that we haven't done, right? So Elixir or R are languages that we don't officially support on Heroku, but you can run them on Heroku because other people have built those build packs based off of the Buildpack API. In addition, there's whole new ways to have different build pipelines, right? The whole entire front-end ecosystem around Node and React and Meteor and all those things, you can just pull down a build pack and use that to build it. There's tools like Nginx or OpenCV that you can just add on to your build pack if you want those tools as part of it. And finally, there's also off-the-shelf software where people have built build packs where you can just do simple configuration and not worry how to actually set up and run and spin up those pieces of software on the platform. And as part of that whole move, there's been other players in the space that have adopted kind of the build pack way of how you actually would build apps with it. For instance, Cloud Foundry is an on-prem solution where they use build packs to build their images that they run in production that you can run on-prem for you. GitLab has a thing for doing building stuff with that for CI and other things where you can have custom build packs. And all the other providers on actually adopting build packs to actually run and be this unified build pipeline for doing that. And so that was build packs, but the reason we're here today is to talk about Cloud Native Buildpacks. And so we've talked about a lot of time on the benefits of the things you don't have to worry about because build packs handle these things for you. And Cloud Native Buildpacks is a project that is about taking those benefits for app developers and combining them with the benefits that we're used to today with all these great things with the container ecosystem. So instead of producing a tarball, we're producing an OCI compliant Docker image. So that means you can use all the tooling with the end result with the Docker runtime that you have today, all the Docker tooling. You could run it in Kubernetes, right? And so that's kind of the big advantage. And so we're not starting from scratch here. We're taking the learnings that both Heroku and Pivotal have had running build packs in production for so long and bringing it into this container ecosystem so we can allow developers to focus on building apps that deliver value to their customers and not as much about operating and figuring out all these other concerns about actually constructing and building these images.
All right, cool story, bro. But I just want to run me some build packs, right? Well, so services like Heroku and Cloud Foundry have been running build packs for quite a while. But if you want to run Cloud Native Buildpacks yourself, you can use the Pack CLI. So this is a project or a tool that's part of the Buildpacks.io Cloud Native Buildpacks project. It's a CLI tool you can install locally, and it provides you with a few commands that allow you to run Buildpacks, manage Buildpacks, and then operate on the images that they generate. So the most important command that's part of pack is the pack build command. So this is a command that will run a build pack, and you run it in much the same way that you would run Docker build on a repository that had a Docker file. But pack build doesn't require any external configuration, such as a Docker file or something like that. You can run it against any arbitrary source code repository, and it will produce a Docker image, and that the image name is the only required argument that it has. So this is what it looks like to run pack build against a Java application. So here I'm running with the Heroku Buildpacks builder image. This is an image that contains the Heroku Buildpacks. And I can use that locally to run against this app, and it will detect that I have a Java application. So it'll identify that, and then it'll run the Java build pack, install the JVM, and do a whole bunch of Java things. The end result is an image, so it exports the things that came out of that build process as layers in a Docker image.
And most importantly, there isn't like specific configuration in that app to specify that it was a Java application that you had to do.
So this blank slide is meant to tell you that that might be all you need if you just want to run build packs, right? So you don't necessarily need to write a build pack or create a build pack to use build packs. Most build pack users are just going to consume a third-party or off-the-shelf build pack. But we do want to go over how build packs work, just so you can better understand what their advantages are. So the first step in the process of running a build pack is detection. During this phase, the execution environment has each build pack inspect your application source code to determine if it's appropriate for that build pack. So in the case of the Java build pack, which I showed, it's simply looking for the presence of a POM XML file, which indicates that this is a Maven project. Other build packs will look for a single file. Some more complicated build packs will look for various environment variables to see if services are provisioned. It depends. The next step is analyze, where the build pack execution environment will take an image from a previous build, analyze the configuration to determine if there are layers that can be reused in a subsequent build. So on a fresh build or a first build, this doesn't apply. The third step is building, actually running the build packs to compile your code, download dependencies, or whatever may be necessary to prepare that application for running in production. And then finally, it exports the results of that build as a Docker image. So taking a closer look at detection, if we have a builder that has multiple build packs, we might have some build packs that are optional, like an APM build pack, maybe a build pack for New Relic, which could install like an agent that instruments your code and reports up to New Relic servers. But you might also have some required build packs, like Ruby, obviously if you have a Ruby app, and maybe Node.js too, because you need it to prepare your JavaScript assets. So each of these build packs will run their detection to determine if they apply to this source code, and they'll produce a build plan, which is some metadata. The next step is analyze, where we can, again, take a look at a previously built image and reuse layers if possible, just by looking at the configuration that's attached to it. During the build step, each build pack that passed the detection phase will be run against the application source code. Each build pack has its own cache where it can put things that it doesn't want to have in the resulting image. So for example, the Java build pack will put your Maven repository cache into a cache layer so that it doesn't have to go into your production image. Build packs can also provide layers to subsequent build packs. So the Node.js build pack can install Node.js on a layer so that the Ruby build pack can then invoke the Node runtime to do whatever it may need to do. So after all of these build packs run against your application source code and compile or download dependencies, we go on to the export step, where we take all of those resulting files and directories and compose them into layers in an image. What's interesting here, though, is that these layers, the build packs themselves create intelligent layers that are mapped really well to your application. They're not defined by arbitrary commands in a Docker file that just result in layers based on whatever order the commands ran in. We'll have explicit layers for your app, for your dependencies, for the runtimes you use, for an agent you might have installed, and then for your base image. So what this means is that when you're deploying your app or you're pushing out an image to production or to a registry, you're only going to push the layers that have changed. So if you have not updated your Ruby runtime or your Node.js layer, those layers do not need to be transferred. It also allows us to do some more interesting things like rebasing.
So the second command that we're going to talk about is pack rebase. And when we're talking about the Dockerfile with day 2 operations, one of the things that you have to do is you have to rebuild your application because the first line in your Dockerfile is that from command, like from Ruby. So if you update that Ruby base image that includes a security patch, like it's going to blow away the layer caching for everything below it. So you pretty much have to rebuild the whole thing from scratch. And one of the benefits of the way that we've done layering with Docker images, because we're not using Dockerfile, is that if the only layer that has to change is the base image, we can just update that image underneath. So similar to kind of the story I was talking about with the stack image on Heroku, it means that if there are updates, say, for like Meltdown that we have to apply from this red Ubuntu layer for this green one where we applied these security patches, we can take all those existing layers, like the tarball example from before, and just reapply them on top of this base image. And that means we aren't rebuilding our entire application. So you're not spending time kind of doing all that work. And the way we get this done is if you look at kind of the OCI or Docker image manifest, is that it's split into a few sections, one of them being kind of the tarball layer, or layers where it has like links to all the tarballs that are actually used for the various layers. And the image manifest actually is just this JSON file that looks like this. And for each individual layer, it has a path to where the tarball is, as well as the size and the checksum. So if we replace these entries for the single layer that we care about, all the layers do not have to be linked. That is an inherent property in Dockerfile. So that means we can just replace this one section for the base image, and now we have a totally new Docker image that represents our existing application on top of the new stack image. So for the example of the 40 apps that took 3 hours to do a rebuild, it means we can cut that time down to minutes instead of hours. Because all we have to do is basically rewrite, like generate this layer and then rewrite this image for the 40 apps, and then we're done. And then in addition to that, when we're deploying this out, traditionally you're going to have to, since you busted the cache, you're going to have to replace all the layers below it. So you're going to get new checksums for everything. But in this case, since we're using these existing layers, we can just push out that one image update. So to kind of sum all this up, we mentioned a bunch of shortcomings when you're using Dockerfile to kind of build this stuff, like the day 2 operations, being app-aware, composability, things like that. I think a big part of one of the things we want to do behind Buildpack is we consider fast as a feature. So when you're deploying out security updates, being able to quickly kind of update images, leverage the layerings with the export of like having layers that map specifically to the application means that we can deploy stuff quickly, which is important when you're dealing with a security incident. And in addition to that, we have a unified build pipeline. What that means is that when you're building an application like inside of a company, you probably have a Dockerfile or a few set of Dockerfiles like for the various applications you have within your company. And there's probably more Dockerfiles in a fleet of like 100 apps than exist in the entire Buildpack ecosystem. And that's because like each Dockerfile is kind of this like special snowflake that you have to modify, even if you're using the same tech stack underneath for your application. Because it might be using a different version of Ruby or a different version of OpenJDK that hasn't been updated yet, right? But in our case, for security and other reasons, when you're looking at a single build pack, when your operations team has to vet like what that build pipeline looks at, it's a much smaller subset of things that need to be examined and kind of vetted through versus every app being its special snowflake of how that app gets built. We mentioned this a bunch of just like the Buildpack being app aware. Like the actual Docker layers that are put into it are ones that are intended by the Buildpack versus ones that are just created because that's how the Dockerfile is written. So we can map those more specifically to your application itself. in addition, we have caching with the caching layers, but also caching that makes sense. So you don't necessarily need to bust your entire cache for dependencies when you make those changes. Like we can just add that single dependency when you've updated it versus rebuilding everything from scratch. And then the Buildpack, because it knows all this stuff about your application, the language, we can provide stuff like the Java ops and things as smart defaults that are built into the Buildpack itself, versus if you pull down the OpenJDK image, it can't necessarily make intelligible sense of like what is specific to your application. And finally, we have composability, and this goes back to the example I was talking about, like these unique Docker files that you have per app. And so since Buildpacks are decoupled from the application specifically, they are these like units that are cohesive that can just be combined together. So like combining the Ruby and Java Buildpacks together to build a single build pipeline there versus the example Joe showed of the multi-stage build of like you have to understand how the Java Buildpack works and the Ruby Buildpack works, or not Buildpack, the Docker images, and then figure out how to combine them that makes sense for your particular application.
Yeah, so Josh Long is a pretty well-known guy in the Java ecosystem. He says he doesn't care about containers. And if Josh were here, I'd tell him that he doesn't need to care about containers because he's an application developer. And that's because Buildpacks are a higher level abstraction. They meet developers where they are, and that's at their source code. So before containers was a thing, in the pre-container era, developers didn't usually have to worry about the operating system security updates and the patches they had to apply to various packages. But it's possible for them to just continue working on their application code, focusing on writing cool features and building value in their applications, value for their customers, and still gain the advantages and the power of containers. And they can do that with Buildpacks. So if you want to try Buildpacks today, you can use the Pack CLI. You can get that from our GitHub project, Buildpack. The Pack release page will have various versions of Pack. There's also the lifecycle, which is the Buildpack execution environment. That's what Pack uses. And there's also a formal specification for the Buildpack API. What's really great about being or working with the Cloud Native Computing Foundation and being a sandbox project is that we can create a vendor-neutral specification for this mechanism. Really powerful and really accessible. If you give it a try or you want to chat us up, we have a Slack, slack.buildpacks.io. There's a general channel, welcome to ask questions. And if you want to take a look at some existing Cloud Native Buildpacks, we have our samples repository, which contains like a hello world example and some trivial examples. But then we have some actual Buildpacks like the Heroku Java Buildpack, which I showed earlier, some Node.js and NPM Buildpack from Cloud Foundry. And then I also have a personal Python Buildpack that's not super powerful, but on Thursday, I'm going to show how I built it and what process I went through to create it. Now, as I said before, most Buildpack users don't need to write Buildpacks, but hey, it's a deep dive session. That's what it's for, right? So we're going to get into how you use Buildpacks. We'll show a little bit more about the pack build command, how that works and how you use it, and then we'll walk through creating a Buildpack from scratch. So that's Thursday at 2:35 over in Tomahawk 5 in the TCC. So thank you very much for coming. Check out buildpacks.io. I'm Joe Kutner. This is Terence Lee. We have T-shirts. If you can prove to us that you are a faithful Buildpack follower, Stephen and Elliot here, they're wearing Buildpack shirts. Come chat them up if you're interested. Thank you.